Welcome back दोस्तों. Let us now discuss Werner's coordination theory. Werner's coordination theory was the first theory to explain the formation of coordination compounds. Werner, by his experiments, formed various coordination compounds like what we have shown here. This is hexaamine, cobalt 3 chloride, and another compound which is pentamine, chloro, cobalt 3 chloride. So these compounds were produced in laboratory by Werner by taking cobalt chloride and reacting with 6 moles of ammonia. So cobalt chloride on reacting with 6 moles of ammonia formed this coordination compounds which is hexaamine, cobalt 3 chloride, and cobalt chloride on reaction with 5 moles of ammonia produced another coordination compounds which is this one, which is pentamine chloro cobalt 3 chloride. So these kind of coordination compounds in which we have coordinate bonds were formed in laboratory by the scientist Werner. Hence scientist Werner is considered as the father of coordination chemistry. So let us see Werner's coordination theory. Werner considered metal to have two kinds of valencies. One is primary valency, another is secondary valency. So what are these two valencies? Let us understand. The primary valency is also called as principal valency. It is also called as ionizable valency. So all these three names refers to one and the same thing: primary, principal, ionization, valency. All these three are same term, which is primary valency, which is nothing but the oxidation state of central metal atom. In a coordination compound, we have central metal atom which is in a square bracket, and the oxidation number of this central metal atom is considered as primary valency. So in this case, what is the oxidation number of cobalt? It is 3. So in this case, we can say primary valency for this compound will be 3, which is the oxidation state of this compound. Then let us consider the next compound. This is pentamine chloro cobalt 3 chloride. In this, again, the oxidation state of the central metal atom comes out to be 3. So again we can say the same thing. The primary or the principal or the ionizable valency for this compound is again 3. So let us first remember this. Metals have two kinds of valencies. One is primary, which is also called as principal, which is also called as ionizable valency, which refers to the oxidation state of the metal. Then let us discuss the next valency, which we have already studied, which is secondary valency. So what does secondary valency refer to? Secondary valency is also called by another name, which is non-ionizable valency, because secondary valency refers to coordination number. So in this case, let us consider the central metal atom. The coordination number of central metal atom is the number of coordinate bonds formed with the ligands. So how many coordinate bonds are formed by the central metal atom? In this case, each ammonia ligand, which is a monodentate ligand, forms one coordinate bond with the central metal atom. So one ammonia forms one coordinate bond, second ammonia forms second coordinate bond, third ammonia forms third coordinate bond. So in all we have 6 coordinate bonds which are formed in this case. So the coordination number of cobalt in this case will be 6. So what is the secondary valency of cobalt in this case? The secondary valency of central metal atom cobalt in this case is 6, because the coordination number is 6. That means if the central metal atom forms 6 coordinate bonds with the ligands. So as we discussed, we have two types of valencies. One is primary valency, which refers to the oxidation number of the central metal atom, and other is secondary valency, which refers to coordination number of central metal atom. Now let us see more points about primary valency and secondary valency. The primary valency, which refers to the oxidation number, is non-directional, because primary valency refers to the oxidation number. So in that case, we do not have any specific geometry or direction. So in that case, we can say primary valency refers to the non-directional nature. Now, after that, we denote the primary valency by dotted lines. So in this compound, the primary valency, which is 3, is satisfied by 3 chloride ions. So we denote these 3 chloride ions by dotted lines, because dotted lines are used to represent primary valency. So we can say primary valency, which is the oxidation state, is non-directional. Secondly, it is denoted by dotted lines. Finally, primary valency is for outside square brackets. So we have chloride ions which are outside square brackets. So primary valency is generally shown outside the square brackets. In the square brackets, we will have the coordination complex. So in the square brackets here, we are denoting the coordination complex, in which we have coordinate bonds within central metal atom and the ligands. So this is all about the primary valency. It is outside the square brackets, so it is outer sphere, or we can say ionization sphere. This part is called as ionization sphere or outer sphere. So these are the points about primary valency. One is, it refers to the oxidation number of central metal atom. It is non-directional. It is denoted by dotted lines. It occurs outside the square brackets, which is outer sphere or ionization sphere. Then let us discuss about our next valency, which is secondary valency. The secondary valency, which refers to the coordination number of central metal atom. That means how many coordinate bonds are formed by central metal atom. So that is directional, because it leads to a particular geometry. For example, coordination number of 2, which is referring to hybridization of 2, refers to linear geometry. As we have seen in chemical bonding, the steric number of 2 refers to linear geometry. Similarly, in coordination compounds, the coordination number of 2 refers to linear geometry. The coordination number of 4 refers to tetrahedral geometry or square planar geometry. The coordination number of 6 refers to octahedral geometry. So we can say secondary valency, which is the coordination number of central metal atom, is directional in nature, because it leads to specific geometry. Then let us discuss more points. It is shown by solid lines. So example, we took the example of first coordination compound in our course, which is K4FeCN6. When we started the lecture of coordination compound, our very first simplest coordination compound we talked about is K4FeCN6. How did we write the geometry of this complex ion? FeCN6 4-. So we had central metal atom ion, which formed coordinate bonds with 6 metal ligands. So 6 ligands in this case were cyanide ligands, which is a monodentate ligand. So 6 Cn- formed coordinate bonds with the central metal atom. So in this case, we have a specific geometry which is assigned. This will be called as octahedral geometry. So here we have shown the coordinate bonds by solid bold lines. So we can show the secondary valency by solid bold lines. For example, in this compound, which is hexamine cobalt 3 chloride, we have 6 coordination number due to the presence of amine group. So in this case, we will show the secondary valency, which is the coordination number, which is the number of coordinate bonds formed by ligands with the central metal atom by solid lines. So one solid line by one ammonia group, another solid line by another ammonia group, third solid line by third ammonia group, fourth solid line by fourth ammonia group, fifth solid line, sixth solid line. So all the secondary valencies, which is the coordination number, which is the number of coordinate bonds formed by ligands with the central metal atom, we show by solid or bold lines. Whereas the primary valency, which is the oxidation number, is shown by dotted lines, which is in this case the chlorine chloride ions. The chloride ions are fulfilling the primary valency, whereas the amine group are fulfilling the secondary valency. Now, in this compound, if we talk about, which is pentamine chloro cobalt 3 chloride. In this case, we have again 5 coordination number due to the presence of 5 amine ligands, which I am showing by solid lines because they are referring to secondary valency. The secondary valency we denote by solid bold lines. So we have 5 solid bold lines here due to the amine group, and we have 1 chlorine which is again in the coordination sphere. It is in the inner sphere. So in this case we will also use this chloride ion. This chloride, which is a monodentate ligand, which we denote by chloro in this case, will also be shown by solid line. This chloro is forming 2 valencies. It is forming, one is primary valency as well as the secondary valency. Hence, specifically for chloro ligand, we are showing 2 kinds of bonds here. One is solid and another is by dotted. Dotted one denotes it is satisfying the primary valency, whereas solid ones denote that it is also satisfying the secondary valency. So this chloro group is satisfying both primary and secondary valencies. Hence I am showing solid as well as dotted line in this case. Whereas the 2 other chloride ions, they are satisfying only the primary valency. So we denote the other 2 chlorine by dotted lines. So one dotted line, another dotted line. So this is how we refer to the primary and secondary valencies. So what are the points? Let me discuss once again. Primary valency referring to oxidation number. It is non-directional, shown by dotted lines, and it is outside the square brackets. We call it outer sphere or ionization sphere. Secondary valency, which refers to coordination number, which is satisfied by coordinate bonds of ligands with the central metal atom. It is shown in bold lines and it is directional in nature because it leads to a particular geometry. For example, coordination number of 2 refers to linear geometry. Coordination number of 4 refers to tetrahedral or square planar geometry. Coordination number of 6 refers to octahedral geometry. And coordination number or secondary valency is shown in coordination sphere or inner sphere. Then, what are the limitations or why the Werner's coordination compound theory failed? Because it could explain only certain elements which form coordinate bonds or coordination compounds, and why coordination compounds has definite geometry it couldn't answer. Just it was given that coordination number of 2 means linear, coordination number of 4 means tetrahedral or square planar, coordination number of 6 means octahedral, but there was no explanation why we have specific geometry. So this was another reason why the coordination theory given by Werner failed. First limitation of Werner's coordination theory, it only explains why certain elements form coordination compounds. Generally only the D block elements, which is the transition metals, form coordination compound, but Werner could not explain why only the D block elements could form coordination compounds. Secondly, as I told you, why it couldn't explain why we have specific geometry related to specific coordination number. It also could not explain why we have specific magnetic and optical properties. So these were the reasons why this Werner's coordination theory failed, and we have another theory which is known as valency bond theory, which came to take place for coordination theory given by Werner. So the next theory which we'll study for coordination compound formation is valency bond theory.